Okay, we did mean, median, mode, standard deviation, right? But statistics is bets, and we're going to make bets, right? And this is tied up with the z-scores, right? The z-score gives a relative position in a standard format. I divide the difference between the average and a number by the standard deviation, and that tells me how many standard deviations out that number is. So that if I have a standard deviation of, well, this is here. I have an average of 12 and a standard deviation of 5. Subtract the number, 7 minus 12, that means this is one standard deviation below its average. And I can do this for any sample. So if I had another one that had a different mean and a different standard deviation, and I also got a z-score of -1, that means it's in the same relative position. So I can go from sample to sample to sample and make these standard measurements in terms of standard deviation. So the standard deviation is the rule. If it's big, then -1 standard deviation down is a long way. So this is standardized values. That's what the z is. Right, so we can make bets on these things. Right. This is what we assume everything looks like. We get a sample, we assume that it's a nice bell-shaped curve, right, which is completely false. Right, but it's not too far wrong. Right? All this means is that deviations from the average that are small are more common than deviations from the average that are large. There's less probability in the tails. And one of the ways this was developed was they were making measurements of stars. And basically they were looking out the window and saying, okay, it's about there. So they had to write down the measurement, and they assumed that they would be close rather than far off. Their error would be small rather than large, but that it could be either direction. That's why we get both ends. So missing on the high side is as common as missing on the low side. But a large error is out here in the tail, and a small error is here in the middle. And so we assume that this is what things look like. And because of that, we have the empirical rule. This follows the standard normal distribution, the bell-shaped curve. So what it says is that one standard deviation down and one standard deviation up covers 68% of this distribution. If we have an observation at random from this distribution, we would expect 68% of the time that it's between one down and one up. And that's a bet. We don't know if it's true or not, but that's the bet. So that if I have a mean of 10 and a standard deviation of 3, my bet is that on this scale, here's 10. If I go one standard deviation up to 13 and one standard deviation down to 7, that includes 68% of the distribution. I always said it was 2/3 because that's easier to remember. And it's basically correct, but it's officially 68%. So suppose this is you're waiting in line at the grocery store or something. Right? Long waits are less common than shorter waits. And sometimes you get up there fast, sometimes you don't get up there quite so fast. So the average time is 10 minutes for whatever this is. Then I would expect 68% of the time to wait between 7 and 13 minutes. Right? And this is pure bet based on a mean and a standard deviation, and the assumption that we are dealing with something that looks like this. If I go out 2 standard deviations, 10 plus 2 times 3, well, that's really good. I go add another standard deviation, I go to 16, and I subtract another standard deviation, and I go to 4. That covers 95% of the distribution. The bet is 1 standard deviation up and 1 down makes a 68% bet. 2 standard deviations down and 2 up make a 95% bet. Right, so now, let's do it this way. Here's 10. This is 13, 16, 7, and 4. This is the average 10 minus 2 standard deviations, the average plus 2 standard deviations, and 1 down and 1 up, and we make a bet. First off, what's the bet that the value we get at random is less than 10? 50%, exactly. Right, this stuff is exactly what you think it is. Right? There's nothing here that's different. It's symmetric around the average, so it's got a 50% chance of being on either side. What's the chance that it is less than 4 or greater than 16? It's 5% left. 95% is between those two, so the chance that it's outside is 5%. What's the chance that it's less than 4? 5%, both ends, right? Less than one end. 2.5. So there's 2.5 here and 2.5 there. What's the chance that it's less than 7? You only need 2 numbers now. We've got 68 here and 95 there. What's the chance that it's less than 7? And if you want, make it less than 7 or greater than 13. Here or there. What's in the middle between 7 and 13? 68. So I have 100 minus 68 is 32. So I've got a 32% chance of being down there or being up there. So one part of it down here is 16. Being up here is 16. I can start cutting this thing up. From here down is 16. From there up is 16%. What is it between 4 and 7? All right, no imagination. All right, I got 16% from here all the way to wherever. And I got 2.5 from there to wherever. What's left to be in the middle between 4 and 7? 13.5. 16 minus 2.5. What's between the average and one standard deviation down? 10 to 7. What's between 7 and 13? 68%. So what's half of that? 34. What's on the other side between 10 and 1 up? 34. What's between 13 and 16? Same as between 4 and 7. 13.5. Right? And this is called the empirical rule because it's approximate. It is all you ever need to know about calculating probabilities with the normal distribution. With an actual table or using Excel, we can get exact probabilities for anything. We can say, what is it between here and here? But with this, we're pretty close. We're making bets, and this is the first cut at it. I say that one standard deviation down and less has a 16% chance of occurrence. One standard deviation up and out has a 16% chance. There to there is 34. What's between 10 and 16? The middle and 2 standard deviations up. 34 plus 13.5 is 47.5. Right? So these are the bets, and this is the first shot at bets that we've got. Get Excel going. Pick a spot. We want equals NORM. And we've got the two main ones, norm.dist and norm.inv. Norm.dist gives us the position in the normal distribution for a number. We put in a number, we get a position. Norm.inv, we put in a position and we get a value. Do norm.dist. And we're going to do the example we just did. We're going to put in 7. The mean, comma, 10. Standard deviation is 3. And we always want cumulative. So you have to put in a 1. If you don't put in the 1, all you get is the probability of a single spot. This is going to give us the area from the left. In all of these calculations, the area starts here. And the normal distribution officially goes from minus infinity to plus infinity. All right, that's a wide range. All right. Practically speaking, you get to 3.5 negative or 3.5 positive. You got it all. But it always comes from this side. So if I put in 7, I would expect to get 16%. Because it's coming from this side. Anything else I want, I have to get by subtraction. If I want more than 7, I have to get this and subtract it from 1. All right, so everything is going to be coming this way. So when I do this, I got 7 is what I want, 10 is the mean, 3 is the standard deviation, and 1 tells me it's cumulative. That means from the left up. And I get 0.158. What did I say it was? 16%. This is pretty close. If I put in 4 equals norm dot dist. This time I'm going to put in 4. Comma 10, comma 3 for standard deviation, and it's always cumulative when we use this. What number should I get for this? 2.5. Empirical rule isn't exact, but it's pretty good. What if I put in 7 and I get basically 16%, but now I want between 7, 1 down, and 13, 1 up. What is it between 7 and 13? 1 standard deviation down, 1 standard deviation up was how much? 68. I want to find that 68. But everything in this function comes from the left. So I have to get what's below 7 and what's below 13 and subtract them. So I need, right here, equals norm dot dist, but this time I want 13. This one is 7. This was 16% below 7. This is going to be what percent below 13? 1 standard deviation up. This is 84. Go back to this picture. Here's 13. How much is below 13? I got a 34, which is 68. I got a 13.5 and a 2.5. So I have each of these pieces below 13. If I add 34 to 34, 68, and then we toss in the 16, it's that plus that, it becomes 84%, which is what we got with the XL function, 84%. So 16% is to the left of 7. 84% is to the left of 13. I need to find out what's between them. I said it was 68. So I need equals this minus that. And I get pretty close, 68%. These functions always start from the left, so that I can't do it like I did with the picture. I said, between here and here, I just add up these chunks. I have to do this using their particular setup. That's why I have to get that minus that, rather than just saying 68%. It's just the way it works in the functions. So here, I have less than 7 and less than 13 with 68% between them. The function always comes from the left. And the cumulative, that 1 that I put in at the end of the formula, means it's adding it up to here. So I add it to 7, I add it to 13, and then I subtract the 2. Right, this is just a peculiarity of the system. It is exactly this picture, except I have to do it coming from here. So this picture here will cover all kinds of bets that I want to make with a normal distribution. This is a very common bet setup, and it's called the empirical rule. Go back to Excel, and here, in this one, I put in 7, 10, the average, 3, the standard deviation, and 1 for cumulative. I have 7. I'm going to calculate the z-score. 7 minus 10 divided by 3 is equal to minus 1. That's the standard normal. I go to Excel, pick a spot, and I do equals norm. This is the one I used where I had to put in the mean and the standard deviation. Here is norm.s.dist. It's the standard normal. And the mean for a standard normal is 0, and the standard deviation is 1. When I make that transformation, this 7 minus 10 divided by 3, I change it to a 0 for the mean and a 1 for the standard deviation. So if I go here, norm.s.dist, I only get one number, a z, which in this case for 7 is minus 1. And I still need cumulative. Now I've put in the standardized score, and I get exactly the same thing. The standard normal uses the z-scores directly. So I calculate the z-score for 7, it's minus 1. I put in a minus 1 for the standard normal, and it gives me exactly the same thing. So the empirical rule is the unofficial version of the whole standard normal table, or the normal distribution. There is another version of this that is a sure thing. And this is percentiles and quartiles. This is the non-normal. This doesn't assume any distribution. And the reason we didn't make more use of this before was that it was hard to do. Now with the calculator or a Excel program, bang, it's no problem. What we want mostly is quartiles. You ever take an SAT test or a standardized test of any sort? When they sent you the score, what was it? What percentile were you in? Were you in the 50th? If you were at 50, half the people scored more than you did and half scored less. If you're at the 75%, which is the third quartile, 25, 50, 75, if you're here, 3/4 of the people scored less, and 25% scored more. This is very common for anything of that sort, and we can have percentiles. We can calculate it in deciles, which are 10%, 20%, 30%. It's just a way to cut things up. But if I do this, if I get a list of numbers and I get the first quartile, I know that 25% of the numbers are less than that, are in here, and 75% are more. Here in the middle, what do you have that's all in the middle that you know already? 50% more and 50% less. What's it called? This is what the median actually is. All right? The median isn't a bet. The mean is a bet. The median says, that's the middle of the numbers I got. No question. Here, 75%. I find in a list of numbers where that 75% is. So I can do this as percentiles, which is what they give you on a standardized test score, or you could do it in quartiles. You use the quartiles because this becomes a very particular presentation, which is called a box plot. And a box plot is from the first quartile to the third quartile is the box. And they draw a box. Anything above that is a line out. Anything below that is a line down. And these are not bets. These are, I've got a list of numbers and this is what it is. There's a calculation that you can do for this. You take the list of numbers and sort them. Then you take n plus 1 and multiply it by the percentile that you want. If this comes up to be a whole number, you take that position. Right? I'm not looking at the numbers, I'm looking at the position of the numbers. But there are at least 9 different ways to calculate this same thing. Because everybody's got their particular slant on it. So there's no, like the mean, that's the mean. You say mean, everybody gets the same number. Quartiles are touchier than that because it's not an estimate, it's an actual value. Go to Excel and we're going to make 1, 2, 3, 4, and I just do this so I have a position for the numbers. This one is equal to the previous one plus 1. It's 5. And I copy that down. each of these is the previous one plus one added to the one before. You can do this with the quartile or the fill command or just add it up. And I want, and the 17 works good. Go to that first spot, and this is more, how do you use Excel? I want equals RAND. I'm going to get random numbers. And I want rand between. And you can type the between or just double click on that. And it will give me a random number between the limits that I specify. And I want 1 to 30. And I'm just making this up. There's no particular reason for these numbers. It's just an example. And press enter, and I get a number. Now I want to copy that formula down to my other places. Okay, you got a list of 17 random numbers between 1 and 30. Go over somewhere, put in a 4, say, and hit enter. What happens to your random numbers? Anytime you recalculate, anytime you change something on this sheet, it will recalculate those numbers, right? Which is a pain in the neck. So we want numbers that won't change, right? In Excel, you can turn off the automatic recalculation, or you can force recalculation. Use a Shift F9, it makes it recalculate. We don't want it to recalculate. Mark the numbers and copy them. Come over 1, and we're going to paste them, but we're going to paste special. And if you go down here, we get a paste values. We want to take the numbers that are here and paste them into that spot right there. And it's already done it. All I got to do is get to it. I paste values. Now, these are not going to change. I just made my example with random numbers that will change constantly. Now I've got a list that won't change. In here, I need to know what the relative position of the numbers is. I have to sort these. I want them smallest to largest because that's the way percentiles and quartiles work. They have to have a list, and the numbers actually don't matter. It's what position are they in. Like the median is in the middle. It doesn't matter what the number is. There's an equal number above and below it. So here, I've got these marked. Go to the sort and filter. It's up on the far right. We want smallest to largest. And because I've got numbers beside it, it's going to say, do you really want to just do these? What about these others, stupid? And I say, no, you stupid. Continue with the current selection. And I have a list of numbers in order now. And I want the median. What's the command for the median? We already did this. Equals MED. MED. It's actually median. Okay, but if you put in MED, the only command that starts with MED is the median. And you can double click on that and choose those values. And it's going to give us the number in the middle. So there is the median. That 4 is nothing. If I did it by hand, I've got 17 numbers. With this formula, I add 1 to the sample size, which makes it 18, and I multiply it by 1/2. I get 9. Here, 1, 2, 3, 4, 5, 6, 7, 8, 9. 17 is my median. And there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 above and 8 below. That's the median. What's the first quartile? I've got 17 numbers. What is the one in the 25% position, the 1/4? I'll go here, equals, what do you suppose the command is for quartile? 25%. QUAR. This is the quartile command, and right here, it's got 2 different ways to calculate the quartile, inclusive and exclusive. It makes a difference when we have 17 numbers. If we've got 2,000, there's no difference in these two. Let's use inclusive. And I got a YouTube video, or it's stuck in the quartile thing, that explains the difference between these two. But it is not important for any real list of numbers. Quartile, mark it, comma, and it says, what quartile do you want? And I want the first. Press enter, and it says the first quartile is 9. 1, 2, 3, 4 below, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 above.